In this video, I'll expose the biggest mistakes electrical engineers make in protection coordination. Yes, you heard me right. The biggest mistakes electrical engineers make in protection coordination. Now, have you ever seen a system trip during a minor fault which leads to shutting down an entire plant when just one feeder should have gone off? In cases like this, most engineers rush to blame the relay. Oh, the innocent relay. But here's the truth. The relay isn't the problem. Your coordination is the problem. So we received information from the relays that electrical engineers blame them for their own incompetency. So we are here for justice for our relays. Stop blaming relays. Your coordination is the problem. Hello and welcome back. I'm Jesse from JP Smart Solutions Ltd. So we help engineers and organizations design, analyze, optimize, and protect their power systems using ETAP software. And as we said earlier, in this video, we are going to be exposing the biggest mistakes electrical engineers make in protection coordination. And we'll also be showing you why ETAP software is the ultimate tool for getting it right. So here's what we'll cover. We'll start with what protection coordination really means and why most people misunderstand it. We do it, but we misunderstand it. There is a reason for that misconception. We are going to be explaining that in this video. Then we'll move into real-world disasters caused by poor coordination, improper coordination. The problem is not that there is no coordination. There is coordination, but it is a poor coordination. Then we move on to how ETAP software simplifies and visualizes coordination. And lastly, we'll be moving into why simulation is no longer optional. It is now compulsory. And remember, this is just a preview, a tip of an iceberg of what ETAP software is capable of doing in protection coordination. So let's jump right into it. Now, protection coordination. What is power system protection on its own before we talk about the coordination of the protection? Now, power system protection is the act of employing a mechanism in order to ascertain reduction in the effect of a fault occurring in the system. Misconception number one. People think power system protection is carried out to prevent the occurrence of a fault. That is wrong. In electrical power systems, faults are inevitable. So we can only reduce the effect, we can only mitigate the effect of a fault occurring in the system. So the fault must occur. Now, when we say protection coordination, it's not just about setting your relays. It's about ensuring that the right device operates at the right time for the right fault, which ensures that the system stays stable and safe. I'll take that again. Protection coordination is about ensuring that the right device operates at the right time for the right fault, which helps us to ensure the system stays stable and safe. So basically, here's the simple rule. When a fault occurs in the system, the nearest device trips, and then the rest of the system stays alive. But here's the harsh truth. Many systems today violate that rule. Why is that? because protection is treated like a checkbox, not a design discipline. Now, let me share a story. One of our clients had a 33 by 11 kV industrial substation, and every time a fault occurred on a single feeder, the entire 33 kV bus tripped. So we were consulted, and when we ran a coordination study in ETAP software, it was obvious. Their relay settings overlapped, which caused upstream relays to operate first. Now, after correction, faults were cleared selectively and downtime dropped by 70%. This is the power of proper coordination. So let's look at this. Now we have this first system over here, and we have the same system on the right. We have different sequences of operation. We have relays on each breaker. Now, the fault is placed on lump 7, which is load number 7 over here. The fault is also placed on load number 7 over here. This axis illustrates the tripping sequence of the system. So the fault occurred on lump 7 and circuit breaker 13 was the first to open. The second to open is circuit breaker 10, the third is circuit breaker 12, and the fourth is circuit breaker 9. This is for this system. We have the same system and then the same location of faults. The first breaker to open is circuit breaker number 13. The second breaker to open is circuit breaker number 9. The third breaker to open is circuit breaker number 8. And the fourth breaker to open is circuit breaker number 7, which is the source. So, in your own perspective, between these two systems, which is more coordinated? Which is coordinated, which is not coordinated, or which is partially coordinated and which is properly coordinated, or are both not coordinated? Okay, now when we say protection coordination, let me explain it using this system. Protection coordination is all about backup protection. So if a particular breaker fails to operate or a particular relay fails to operate, the next relay or circuit breaker should operate to isolate that fault. So in this case, we have these two systems. So we have the fault at this location. Now let's assume on both cases, circuit breaker 13 is the first to open, which is the right operation. It is the correct operation. It is the first to open based on the location of this fault. Now, where we have the discrepancy is from the second breaker to open. Remember, we said protection coordination is all about primary and backup protection. So here, in this case, the primary protection is correct, and over here, the primary protection is correct. So if we say it is a backup protection, then this simply means that if circuit breaker number 10 operates as the second circuit breaker, then it is not correct. It is not a backup protection. This is one of the misconceptions people have. People say, oh, so we are talking about isolating the fault and the rest of the systems should remain in power. So if we are saying that we should cut off this guy like it is on this system, if we are saying this guy is correct, then we are isolating the fault, and these guys that do not experience fault are automatically cut off from supply. Now, there's a very small difference between protection coordination and fault isolation. In an ideal case, we are not expecting our relay to fail. We are expecting that a fault here should be isolated by this relay and circuit breaker 13 as seen in both cases. But in a situation, what if this relay is no longer functioning properly? What if something happens and this relay does not react to this fault? The backup now, if it is this guy, then the fault is not clear, the fault is not isolated, because the fault is moving like this. So it's coming to the bus bar, and that is why the ideal case is to knock off this guy. So looking at it, we can say allegedly that this system looks coordinated, while this is an example of improper coordination. I said allegedly here. Now, the reason I said that, we'll get to it as we progress. Let's talk consequences. Consequences of poor coordination. Now, poor coordination leads to system-wide blackouts from local faults. It leads to equipment damage because the wrong relay operates. It leads to unnecessary downtime, which results in losing thousands of dollars per hour. Remember, profit is very important. Then it also results in loss of confidence, because if your protection scheme is not adequate, it's not properly coordinated, operators start bypassing your protection altogether, because you're having nuisance stripping. Now, let me give you a famous case. A refinery suffered a total shutdown due to a 0.4 kV fault, a fault on their 0.4 kV bus bar. But the main 11 kV breaker tripped before the feeder breaker. So production losses ran into millions, unnecessary downtime. And all this is because someone skipped proper coordination. Now, misconception number 2. Protection in power systems is not just about settings. It's not, oh, I've put my pickup settings, I've put the time dial settings, time multiplier settings, I should be good to go. No. Protection coordination is about selectivity, sequence, and time of operation. Now, in the earlier illustration we had, where I said the system looks coordinated, allegedly, we could see the selectivity, we could see the sequence, but we could not see the time of operation. So if your TCC, time current characteristics curve, overlap, then you're one fault away from chaos. Now, let me switch over to ETAP software and illustrate how the software makes protection coordination very easy. So I'll switch over to the software, and here we have a system. We have the power grid, then we have a bus bar, we have the breakers for the transformer. Here we have a differential protection scheme for this transformer. It's a 5 MVA transformer to a bus bar. So this transformer steps down the voltage for this section, and we have motor loads over here. So we have our switch gears, we have our relays for each motor, we have relay for this cable, we have a relay differential protection scheme for this transformer. So these are basic overcurrent protection schemes, and we can test and simulate to see how the system operates when there is a fault. So just for instance, we can view the relay settings. So this is the settings for this particular relay, and each of the other relays have similar settings. So we can take this entire section, okay, and we come over here where we have create star view. Let's see what our protection coordination really looks like. Okay, so we can zoom in our one line diagram and we can bring it out over here. So we can see our motor starting curves, we can see our relay curves, we can see the motor damage curves. So from this TCC, can we tell, is our system properly coordinated? Is it properly protected? You can take a wild guess. But let's not jump into conclusions. Let's simulate. That's what the software is here for. So let's say I insert a fault at any of these. Okay, let's use this motor. We have a fault on this motor. And we can see sequence of operation relay 1 CB1, relay 4 CB4, relay 5 CB5. They are all tripped by overcurrent 51, so time overcurrent protection. So we can see the sequence 1, 2, 3 over here. So in this case, can we say that the protection coordination is accurate? The selectivity is there. Okay, let's see if the fault is on this section. Okay, we can see 1, 2, 3. All right, let's put the fault on this motor. Okay, so we are inserting 3 phase faults at various locations, and we can see that the selectivity is there. Let's have the fault on this bus bar. Okay, okay, okay. So we can see it's working in the right sequence. Let's have it over here. Okay, okay. And let's have it on the transformer. Okay, in this case, the differential protection kicked in 87 instead of overcurrent protection because the transformer is being protected by a differential protection scheme. Now, in this case, can we say that this system is properly protected and coordinated? Looks good, right? Now, we mentioned some parameters. We said selectivity is 1. Aside looking at the system, we can tell that this system is good in terms of selectivity because the coordination sequence looks good, allegedly. Now we come over here and we look at the time of operation. We can see that this relay is taking 789 milliseconds to operate. So it is at this point we now need to checkmate this guy by creating a TCC with that relay to see how the system operates. Okay, we have a fault inserted on the system, so that's why we are having this guy. All right. So we can create a star view. Okay, so now we have the motor. This is the motor starting curve, and we can see this is the relay curve. So I'll leave it to you to decide, is this system properly coordinated or not? Is that time of operation too much or too less? Should it be increased or should it be decreased? So in your opinion, is it properly coordinated or not? So ETAP software helps us by showing the sequence of operation. It shows us overlaps or miscoordination. It shows us recommended adjustments if we are having miscoordination or improper coordination. You can easily drag curves, you can adjust settings, and you can instantly see if your coordination improves. No guesswork. No trial and error in the field. So ETAP software helps us to simulate everything before we even energize the system. Now in our professional trainings, we go deeper, much more deeper, like how to select curves, IEEE, IEC, set your time multiplier settings, and even coordinate your low voltage breakers with upstream high voltage relays, and much more when it comes to protection coordination. Now we'll be switching back to our PowerPoint. All right, we are at the final lab. So before this, part of our outline said why simulation is non-negotiable. So in modern systems with distributed generation, inverters, and complex loads, manual coordination is no longer enough. Simulators like ETAP software are not luxury, they are necessity, because protection isn't static. Your system changes, load grows, sources will shift. For example, you can have an on-grid solar PV system, or you can have an off-grid solar PV system with a backup generator. When the generator is supplying power, the source has changed. When the solar PV system is supplying power, the source has changed. You can even have a hybrid system where you have solar PV systems incorporated with wind turbine generators. So in cases like this, your relay settings that worked last year may fail today. Yes, it was perfect last year, but it may fail today. So without simulation, you are designing blind. Stop guessing. And most importantly, electrical engineers, stop copying settings from old projects. We cannot emphasize this enough. Power systems are dynamic in nature, they are not static. And you know, the problem with this is when you copy settings from old projects, you do not even realize you are making a mistake, because electrical power systems help engineers cover their errors. Now, you design your protection coordination scheme and all that, and then you implement it in the relays. But then there's no fault for, let's say, the next 3 to 6 months, and then a fault occurs. No one will come and hold you and say, oh, your protection scheme was inadequate because it worked for a period of 6 months. So it only takes an organization that carries out root cause analysis and very serious, very serious interviews to find out what is the actual problem that caused this. So when they realize, oh, you just copied the settings from old projects, and that is the overlap we are having, causing nuisance tripping in our system. So stop copying settings from old projects. Your system deserves a tailored, validated coordination. So here's the bottom line. Protection coordination is not optional. Wrong coordination causes blackouts and damage. Yes, it causes damage too, because if the breaker fails to operate or the relay fails to operate, that equipment may be damaged. ETAP software gives you the clarity and confidence to get it right. Now, if you found this valuable, imagine what you gain from our professional training, where we walk you through real-world projects, hands-on exercises, and professional grade reports. Remember, do not design by guesswork, design by simulation. If you wish to join our professional training, feel free to contact us using these details. You can call us on this number, or you can send us a WhatsApp message using this number, or better still, you can send us an email using this, or you can drop a comment in the comment section and we'll respond to you as quick as possible. Thank you so much for watching, and we'll see you in the next video. We remain JP Smart Solutions Limited. Stop blaming relays. Your coordination is the problem.